Hi, everyone, and welcome to this evening's webinar. I am Dr. Brennan Huey, the Department Chair for the Physics and Astronomy Department in Prescott, Arizona. We have two majors here, the space physics major and the astronomy major, both focused on astrophysics and related fields. Today, we wanted to highlight a particular focus of our department here on the Prescott campus, which is the relatively new field of gravitational wave astronomy. This is a whole new branch of astronomy that's only about a decade old. So before we get into our presentation, we want to first look at a video that's going to highlight Embry-Riddle in general. So if we want to play that video. So there's a couple takeaways there. Everything you're seeing there is very hands-on. Everything there is very focused on aerospace. So in our department, we're very much focused on the space side of aerospace, as you'll see in this presentation. So today we're going to have a main presentation by Dr. Michaela Zanelin and shorter presentations by Dr. Ellie Grederson and our undergraduate Alice Tucci. So that's going to be basically the bulk of the presentation, and then we are going to take questions afterwards. So as the speakers are presenting, I highly encourage people to drop questions into the chat. Rather than raising hands, we're just going to have questions in the chat, and then we'll have a Q&A after all three of the speakers are done. After that, we will also have a presentation by admissions with details on how to apply to Embry-Riddle if you're interested. So today we have a long-standing physics professor, roughly 20 years here at Embry-Riddle, Dr. Michaela Zanelin, assistant professor Dr. Ellie Grederson, who's been with us for 3 years, and one of our juniors scheduled to graduate next year, Alice. So why don't we start with Michaela's presentation and take it from there. So if you want to go to the next slide. All right, Dr. Zanelin got his PhD in Italy, but got started in gravitational waves at MIT. He's been involved in various aspects of LIGO and gravitational wave research for the last couple of decades, but I'm going to let him give some more details about that. So why don't you take it away, Dr. Zanelin?
Yeah, thank you. So welcome everybody, and I might give a little bit of the background on my past while we go during the presentation. But the main point I wanted to convey from the very beginning of the presentation is that the field of gravitational wave astronomy is the new continent, if you want, that has been discovered in fundamental physics. I know if you Google what is the most important physics discovery of the 21st century, and I tried to do that a couple of days ago, you're going to see gravitational waves, and we have a big role in that. I was privileged to spend 8 years at MIT with what many people consider the fathers of the field, Ray Weiss, that he got the Nobel Prize in 2017 for this. But here in Prescott, we have one of the largest group in the world with 4 professors, two other professors that are supporting graduate students. So I'm very excited to share this new field of research, and hopefully you will be excited too, because I know we have a lot of good opportunities going on here. So if we go to the next slide. So this is a little bit of a historical slide, because when you do astrophysics, you also study the past. This is a Chinese drawing from 1054. It was the first supernova that was recorded by any person in official document. This was about 1,000 years ago from a Chinese astronomer, and 1,000 years after, we pointed the telescope there and we found the traces of the Crab Nebula, and we were able to track down that it exploded exactly in 1054. And now we search for gravitational waves from the Crab Nebula. So this is, you're going to see the story going back to the beginning from when I start here. So let's go to the next slide. So So many of you might have heard about gravity, several of you might have seen in school this equation. And this was derived from Newton, and it's useful in many ways. People still use it for the motion of satellites, but it doesn't tell you the whole story. And if you go to the next slide, and in 1915, Einstein came up with a big revision of what is gravity, and instead of having the equation that you saw in the previous slide, he came up with a set of equation that implied that space-time is actually a medium that can vibrate, can be deformed, and the motion of the planet, or anything in this medium is given by the interaction with this medium. And the theory of general relativity is very beautiful, and some of you will have the chance to study that. Now, you have two types of deformation of space-time. You can have a static deformation, like the one produced by the sun that helps the planet to move along the trajectory they have. But you can also have something that is dynamical deformation. So if you go to the next slide, and this dynamic deformation are deformation that in a certain position, a certain time, they are different. And this is a pictorial description of which kind of deformation general relativity predicts from two black holes dancing around each other. And this was a dream by many that you could try to detect them. And Einstein itself believed that it was too hard to achieve. And hopefully, I know, likely he was wrong with that. Let's go to the next slide. And this is a little aspect to how history goes. I know if you want to ask $1 billion, like the money that we needed for the first measurement and the first experiments to detect the gravitational wave, you want to prove that you know what you're doing. And this was an observation of a binary system that if you use Newtonian equation, the two stars are supposed to have the distance, they stay constant with respect to each other. But if you use general relativity and the prediction of gravitational waves are expected to take energy away, and the distance is supposed to decrease over time. And so in this plot to the right, you have that the horizontal line tells you that what would happen if the distance is constant. The blue line is what happens if the distance changes, and the red dots represent experimental measurements. And so people, Holtz and Taylor got the Nobel Prize for this discovery. There was an indirect evidence that gravitational waves exist. And at that point, people decided to support the construction of LIGO and try to detect these waves directly. Let's go to the next slide. And gravitational waves, as predicted by general relativity, the effect they have is that if you have a ring of masses, they're going to deform it a little bit like the way in the amusement parks, those mirrors can deform it. They can shrink in one direction and stretch in another direction. If you go to the next slide, and you can quantify this deformation. I know on the left, if you have L, which is the radius of your ring, and on the right you have delta L, which is how much this is deformed. For gravitational waves of astronomical events similar to the one I just described, this delta L over L is a very tiny number, 10 to the minus 21. So tiny that's why it took 100 years before we found a way to measure it. And the key of being able to measure it is the discovery of lasers, because they have a very small wavelength, very stable wavelength, and there are a lot of formidable challenges and technological advances that had to happen to make this a reality. If you go to the next slide, and the way we were able to make this a reality and is to build this gigantic laser system that have an L shape, and you have cavity inside. You have laser beam moving back and forth, and we are playing with the interference of these laser beams. And this one is a little bit of a drawing of superimposed one of the laser interferometer. This one is in Livingston, Louisiana, with one of the gravitational waves deformation. And the idea is that the laser beam going in one direction is going to experience a stretched space-time, and the laser beam going in the other direction is going to experience a contracted space-time. And so the interference between the reflected laser beam is going to be affected by this stretching, and we would see an effect in the light that we see when we recombine the two laser beam. Let's go to the next slide. Now, as I said, it is very important to understand the orders of magnitude of what we're doing here. I know those arms are 4 kilometers, order of 10 to the 3 meters. I know if we have a strain, I know which is a deformation, 10 to the minus 21, it means you are trying to measure change in distances of 10 to the minus 18 meters. I know this is many orders of magnitude larger, smaller than the diameter of a nucleus. And so, as you can imagine, there are very sophisticated and advanced technique to make it happen, but we were able to make it happen. And if you go to the next slide, and what I mean we were able to make it happen is that in 2015, we were able to record, and the signal are here on the right, the dance of two black holes dancing around each other. And this was something that happened, I know, 750 million years ago. And this was considered by the New York Times the most important physics discovery of the last 100 years. And in the paper that was awarded and the Nobel Prize, there was only one undergraduate student, and he was from Prescott, because here we involve undergraduate students in actually forefront research. Our undergraduate students, they work with professor in publishing papers. I spent a lot of time at MIT and Caltech, and I can tell you that I know undergraduate students, they don't see the real research very much. They have some exposure, but here it's a core part of what we do, and we were able to expose them in many ways to this kind of research. And these actually were ended up in wonderful careers. The student that was co-author here then went to the PhD at Harvard, but one of the students, the group, is now a professor at MIT. Other students went to Stanford, Georgia Tech. So we are very proud of our students, what they are able to do after. Next slide. So this is our artist description of how these two black holes would have looked if you would have been close enough. And one of the things I wanted to stress is that gravitational waves have the capability to map out distribution of mass in the universe that don't emit light. And stars only make 3% of the mass out there. So gravitational waves literally are opening a new era of astronomy where we can actually map out better the rest of the energy out there. Next slide. So this is a picture of the three gentlemen that got the Nobel Prize. Ray Weiss, that was my boss at MIT, and the other two scientists at Caltech, and they were very kind because they talked about how the Nobel Prize was the fruit of all the people working on the project, including the undergraduate students. Next slide. So since the first discovery, we've been able to detect hundreds of gravitational waves of different shape and different forms. And you can also find online people that play the sound that corresponds to that. In some regard, we have been looking at the symphony, if you would consider what happens in the universe as symphony. And now with gravitational wave, we can also listen to the symphony. And the field is expanding enormously. There have been investment and commitment from many countries for $5 billion. And so this means that there will be also job opportunities for many scientists in the future. Next slide. So here now I have a few fun slides, and Ellie and Alice will say a little more about it. These are pictures of how these instruments look inside. I know you can see mirrors, you can see different parts of optics, and it really looks cool scientist, and it's such a joy to be able to work on any aspect of the science. There are many aspects, from theory to data analysis to experiments, and in the group here we have about 15 to 20 people depending on the year, And so you would have a lot of opportunity to enter in many different aspects of the research. Next slide. So this is the control room. And for people that watch the movie Interstellar, Kip Thorne is one of the people that wrote the script of the movie Interstellar and wanted the movie to start with a signal given to our interferometer from an alien civilization and received in our control room. But then I know Nolan said, I don't want it to do just relate to gravitation wave because I don't want to risk that only gravitation wave people go and watch it. But I know it's a cool place, and our students have the joy sometimes to go there. Go to the next slide. This is how they look, some of these interferometers. There are two in the US. The one to the bottom left is in Italy, and Alicia hopefully will go there this summer. And the one to the right is in Japan under a mountain. And we have opportunity for summer internship for people to go there. And usually they are paid with NASA or other kind of funding or NSF. Go to the next slide. These are the location around the world. Pretty much we use the planet as a giant sonar array, and these are all the different microphones. And the one in India has been constructed. These are the current generation of interferometers, and then there is a future generation of much more sensitive that will be able to detect merger of black holes in the past further than the formation of the first stars, which would be able to, I know, verify the hypothesis that black holes are formed with the supernovae, or if some of them are formed directly from the Big Bang. So it's a very intriguing possibility for the future. Next slide. So the one to the right is one of the nerds from our group. His name is Josh, and Alicia works with him, and he is currently in one of the interferometer in Hanford in installing an improvement to make this interferometer less sensitive to ground vibration and to control electronic noise. And so he's having a lot of fun, and it's also useful for the collaboration. And in the background, you can see part of the things he's assembling. So next slide. This is just a couple of slides on some of the things he's doing. He's installed a laser system that is trying to keep the motion of two tables synchronized with respect to each other instead of in a random way, in such a way that we don't accumulate undesired phase differences. And this is something that we will probably install for different parts of the instrument. But I know these are elaborate instruments and beautiful elaborate instruments. Next slide. For people that already know what is the Fourier transform, this is a description of the noise as a function of the frequency, and the two arrows indicate the area where Josh is working on. Okay, next slide. And these are some of the students that I took last summer to visit the interferometer in Pisa. The one that I'm hugging right now is he just became a professor in his hometown in Warsaw, and he is very, very happy about it. The one next to him with the beard is now a PhD student in Oak Ridge National Laboratory in the largest supercomputer in the world, simulating the gravitational wave from core collapse supernovae. And some of the others are still with us. Next slide. This is some of the picture from Pisa, and I'm actually taking students to visit that this summer. Sometimes in the summer, I organize a study abroad to visit the antimatter factory at CERN, and then I also take students to visit the interferometer. Next slide. And I just wanted to say a couple of comments about the theory aspect, and some might say what creates gravitational waves. Well, you need to have a special type of motion, which is called quadrupole motion. A sphere that is expanding is not sufficient. It needs to have the shape of the object that needs to change. And the neutron stars are one of the examples, the merging neutron stars or merging black holes that I mentioned, but there are other examples. And in our group, if you go to the next slide, in our group, we have a specialty of a gravitation wave from core collapse supernovae. I know this is one of the equations that is described the key equation to calculate the gravitational waves. I know it's an integral of an energy density. I know for people that understand what is a quadrupole, they will recognize that this is related to the moment of inertia of a rotating object. Next slide. So this is my last slide, and what I wanted to say about it is that I started this presentation talking about an undergraduate student that did something exceptional, being part of the paper that got the Nobel Prize, and I wanted to give another example to see that this is a track of what our students do is not an exception. This is Colter Richardson that graduated in 21, and he continued working on a project that he started here. And last fall, he found a way to use gravitational wave data to detect scars in the fabric of space-time produced by core collapse supernovae. This project made the front page of the National Science Foundation. So it's absolutely marvelous, and obviously makes you happy like a parent. And in some regard, I know I'm very proud of all the students that are involved, and we often have also high school students that are involved in what we do. Currently, I have a high schooler that is spending a full semester doing research on supernovae uh, science for LIGO. So occasionally we have high schoolers as well. Okay, and that's the end of my part. Thank you.
Thank you very much, Dr. Zanelin. So we're going to have a couple of shorter talks highlighting different aspects of the kind of research doing with LIGO and gravitational waves. So next up, we're going to have one of our four faculty involved with LIGO on the Prescott campus, Dr. Ellie Grederson. She's been with us for about 3 years, but she actually did her undergraduate here, and is now back because she couldn't stay away from Prescott campus. Between then and now, she did her PhD in optical sciences at the University of Arizona, and she spent some time as a research scientist at a couple different government labs, which gives her some unique experience compared to a lot of the faculty that she, brings to classes and research and the like. So, Ellie, why don't you go ahead and talk about some of the more hardware aspects of LIGO?
Okay. Yeah, so I'm an experimentalist. I work on optical systems. So go ahead and go to the next slide. I'm going to tell you a little bit about what we do in our LIGO Optics Research Lab. So those are two of our research students pretending to work on something for the photo op, but yeah. Next slide. So Michaela Zanelin went over what the interferometers are, how they're the two different arms, and we're trying to measure an arm length difference that is smaller than the size of an atom. So how are we able to do this when the mirror that is at the end of these arms reflecting the light back is made up of atoms that are all in a thermal bath, they're all warm, they're moving. And we can play a couple of tricks to do this. So one of the tricks is that we have very high optical power, so a lot of photons reflecting off these mirrors. And we also have very large mirrors so that we can average out the movement of many, many atoms across the mirrors. So you can see in this picture off to the right-hand side that it is about a 40 centimeter mirror. And there is a hand in the lower corner there for scale. So you can see these are really large and we use that full surface area. It probably doesn't look like any mirror you've ever used or seen. If you look at your bathroom mirror, those are usually 90–95% reflective across most of the visible spectrum. So we don't usually need things more reflective than that. But for this, if we don't have a high reflectivity, then we're going to lose all the light that's in those arms and we're not going to have as good a measurement. So the mirrors shown here, all of the mirrors in LIGO are more than 99.99% reflective, but for a very specific wavelength, which is a little bit redder than the reddest we can see. It's in near infrared, it's 1064 nanometers. And the way we do this is these mirrors are made up of a lot of very thin layers that each layer reflects a little bit of light and those interfere constructively to reflect back the light. So it isn't reflective in the visible, but it is extremely reflective in the infrared. Okay, next slide. So I work on these mirrors, characterizing these mirrors. The one that's in LIGO right now is in that upper left picture. What I work on are crystalline mirrors, which are new technology. It came up about 2014 or so, I think, is when they started producing these. So it's a fairly new technology, and it's one of the candidates for future upgrades. You can see a picture of those in the lower right-hand corner with they kind of look gray in the visible, but again, they're super reflective in the infrared. And the way that these are made is that they're grown as a crystal. So they're grown on a seed crystal, they're peeled off, and then they're flipped over and stuck onto the substrate that we're interested in. And we like these because, as I mentioned, when you have a bunch of atoms in a thermal bath, they're going to be moving, and that movement creates noise in the system. It's one of the limiting noise factors in the center of that uh, sensitivity bucket that Dr. Zanelin was showing us earlier. So by putting the atoms into a crystal structure, you have much stronger potential well that they sit in. And if they try and move, they have atoms next to them that push them back into place, and you get much less movement, which means that translates to lower coating thermal noise. But there are some issues that, because it's new technology, there's a lot of things that we're still trying to understand about these coatings. So next slide. One of the main things our lab looks at is what's called birefringence. So birefringence is what happens when it reflects back different polarizations of light with different phases. So light's a wave, and depending on which direction it's wiggling, we call that the polarization. And when we get the light reflected back, if one polarization has gained a slight amount of phase compared to another polarization, that adds noise to our system. If it's even across the entire surface, then we'll just choose one polarization, and that's fine. But if there's variation in the birefringence across the surface, that can cause us problems. So in the right-hand picture here, you can see one of these gray mirrors sitting on a translation stage. That's actually the largest mirror of this kind that's ever been created, and it's in our lab. We're measuring it. And then this kind of orangish top picture, you can see this is a comparison of the two different polarizations, and you can see that there's a lot of structure here. And part of what we're doing is we measure the birefringence and we see structures like this, and then we go back to the company and we say, well, we think this is what's going on. Can you test a different mechanism? In this case, the top image, I said that we pull off these coatings and we stick them to a substrate. It looks a whole lot like when you put your screen protector on your phone, and it kind of starts in one place and then you see that bond wave traveling out across the surface. In this top picture, that's exactly what happened, but they started the bond in the very center of the disk. And you have a curved disk that's trying to conform to a flat substrate. So if it bonds in the center, what we think happens is if it bonds in the center, it's trying to conform to that flat substrate, but it can't slide across the surface because it's been bonded down. So the only way for it to conform to that flat surface is for there to be a stretch in the material that stays in that material, and we think that's what causes these big rings. So in the bottom picture, we had the company make a second one where they started the bond at the edge, and you can see we don't have those big rings. So we've solved one manufacturing problem, but now you can see that there's other structures that we're looking at, and we think those kind of three areas have to do with how it holds the coating, and it's just an iterative process to try and make these coatings both large, because this is about the only application that needs these giant coatings, but also defect free. Okay, next slide. So two other things that we worry about are scatter and absorption. And we work with other groups at Stanford. They measure the absorption for us at for LIGO. At Bard College, they measure scatter. And at our university, we look at different defects in the coating under a scanning electron microscope. So in these upper and left four images, you can see the little arrow shows a 2 micron size. That's about 2 microns for these images. Average human hair is 50 to 100 microns. So these are incredibly small. In the upper right-hand corner, you can see that this defect, you can actually see all the coating layers in there. And we're trying to correlate with these scatter and absorption measurements to understand what effect all of these defects have, and hopefully start to understand from their shape what's causing them. Um, on scatter and absorption, there's both background absorption and scatter, and from these point absorbers. For the with scatter, if it's scattering light out, that's not good because we're losing power. But if we have light that scatters back into the interferometer down the path that the light's traveling from, then that's going to interfere with the signal that we're looking for. With absorption, um, we have the added effect that if you're absorbing light, which all these materials do to some level, then that energy has to go somewhere and that turns into heat. So when you heat up these coatings, they're going to change shape. They're going to thermally expand. So with the background measurements, which is even across the coating, we can deal with that by doing things like heating the coating in various ways, shining another laser at it that has the opposite beam shape to our measurement beam, and heating the coating to counteract that. But with these point absorbers, what happens is you get one point that heats up more than the rest, and you're going to get a little bump on the coating, and it's not going to reflect back the correct shape of light, of beam shape. Also, if they absorb too much light, remember we have huge amounts of power in these arms. If they're absorbing too much light, they can burn. And this lower right-hand picture is a picture of what happens when, during one of the absorption measurements, the laser they were using hit one of these high absorbers, and it burned a pretty big chunk, and then that caused the areas around it to deform and start absorbing, and it just continued out and made this pretty catastrophic damage, which the bottom of that, you can see the scale is quite a bit larger. You can see this by eye. So that's kind of worst case scenario. We can't have any of those in the interferometer when the final mirrors are made. So these are some of the things that we think about when we're looking at potential new mirror coatings. Um, Alrighty, next slide. So a lot of these measurements and characterizations trying to understand, either develop new coatings or understand the coatings we have, they're all done on tabletop experiments in labs like ours, at universities all over the country. So these two pictures are two pictures of different experiments we have in our lab. I like to say optics is a little bit like Legos, and that you have all these pieces that go together in a certain way. We have these specialized tables that reduce vibrations, and we're able to set up our experiments on. Next slide. One thing that is really unique about our university is that we only have undergraduate researchers. So these are the four undergrads that are currently in our lab. And how do we get these students to be doing what is, in some cases, graduate level work as an undergrad? A lot of it is working with them to find what their aptitudes are. So Ambrose and Naomi are two seniors. Ambrose is really good. He's an engineering major. He's really good at tinkering with things. He likes to get the translation stage going, and he wrote all of the programming for the data acquisition system that talks to the translation stage and gets that whole system working together. That's something he was really good at and what he was interested in. And so he was able to make a lot of progress. Naomi came into our lab. We had her set up a readout system for one of our experiments, and she wanted to understand it really well, so she created a really interesting mathematical model for this readout system, and hopefully she'll be publishing a paper on that by the end of the year. And it was just what she was interested in. Atticus is a junior this year. He started working with us as a sophomore, and he is interested in the hands-on aspect. He's been building a custom spectrometer, so he's designing the optics chain. He's also been recently designing the electrical system, so he's building a circuit from component parts. And Ari started with us as a freshman. They're really interested in the mathematical side. So what they've been working on is the calculations to manipulate the shape of light to match the experiments that we have going on. So we take a lot of time trying to understand what each student is really interested in and focusing their work on something they're good at. I encourage you guys, if you're interested in any of the research that you see whenever you get to university, never feel like it's too early to go and start engaging with the lab, asking questions, trying to understand if it's something you want to do long term. And there's always something that you can start doing. So the earlier that we have you starting working on a project, the more progress you'll be able to make by the time you're a senior. If you start as a freshman, you're not going to make progress as fast as a junior, but that's okay because you still have that year ahead of you. So I highly encourage you guys to come and talk to us early if you see anything interesting. Alrighty, and I think that's it for me. So.
Thank you, Dr. Grederson. So we have one more presentation. You've heard a lot about the importance of undergraduate research at Embry-Riddle Prescott. So we wanted to feature one of our undergraduate researchers who's working with Dr. Zanelin. We're getting great questions in the chat. Please keep them coming. Why don't you please take it away? Please go ahead and get started.
Yeah,
Oh, okay. Hello, everybody. My name is Alice. I'm a junior here at Embry-Riddle. I'm also part of the volleyball team, and today I'm going to talk to you about what I do for research briefly, and I'm also going to help answer any questions that you guys may have as a student here. Okay, we can go to the next slide. Okay, the title of my research here is Noise Reduction in the Low Frequency LIGO Detectors. Dr. Zenelin already explained a good amount about gravitational waves and LIGO. And for my research, we are particularly interested in the low frequency range because that's the range that the core collapse supernovae emit. And for you guys to have an idea, the LIGO detectors are extremely sensitive because the gravitational waves are very, very weak. So they have to be very sensitive to be able to detect them. But because of that high sensitivity, they end up detecting a whole bunch of other noises, and that can interfere with the results and what's detected. For example, if there is cars driving nearby, if there's an airplane going over the observatory, the detectors are going to cap that. So we are interested in reducing that noise with the use of control systems and coding to make the detection go by smoother. For our experiment, we have an experimental part, and then we also have a coding part. So you can move on to the next slide. For our experimental part, we have that model set up. It's pretty much a smaller scale of LIGO. The picture on the left shows exactly what it looks like. We have a pendulum, a Cavendish torsional pendulum inside a vacuum chamber. And then we also have an optics model consisting of two lasers, two photodiode detectors, and a bunch of mirrors and lenses. You can see that it's color coded in the picture to make it a little easier. The laser that is in pink is going to provide some power that will hit the pendulum, and that it's going to kind of move the pendulum around a little bit. And then with the laser in red, the laser beam is going to go around the whole model. And that's the power that we end up analyzing. Can move on to the next slide. Okay, so you guys have an idea. I will explain the path that the laser beam makes. So when we turn it on, the laser will go straight and hit a mirror at the bottom of the vacuum chamber, like under the vacuum chamber. Okay, you can move on. After that, the laser hits that mirror, it will be directed up and into the vacuum chamber. And pretty much there is other mirrors that are going to direct the laser beam to the pendulum. There, it's kind of hard to see the pendulum there because of the vacuum chamber, but there's a picture of it outside. That's what our pendulum looks like. We just don't use the two big masses. And we have a mirror in the very middle of the pendulum, and that's where the laser beam will hit. After it hits the pendulum, it will make its way out of the vacuum chamber through another mirror. It will be reflected down, and then you can move on to the next slide. It comes out and then it goes through a lens to be so the laser beam can be like focused again. It will go into the beam splitter, and then you can move on to the next slide. That beam splitter makes the laser beam be split into two. So part of it is going to keep going forward and hit one of the photodiode detectors, and then the other is going to be reflected 90 degrees and go hit another photodiode. We have two because we analyze the power output from the split laser beam, and then when we combine the analysis of both of them, we can get really good information, really important information about the pendulum and the movement that it makes. You can move on to the next slide. We have our photodiodes plugged into a computer, and we use a computer program called Picoscope. And this is pretty much what I see after I hit the button to collect data. I leave it running for a few days, 3 days. And when I come back to the lab, I leave the lab so it's nice and quiet. And when I come back, I open it. This is what I see. The red line, I guess, is from one of the photodiodes, and then the blue line is from the other one. And I find this particular graph really interesting because you guys can see that at the very end, there is a like very big boom in how it looks. This is just an example of how sensitive it really is, because I made this collection over the weekend. So it was really like during Saturday and Sunday, there was nobody here at school. We got nice concentrated data, and then that little piece that got very big is from Monday when there was people around. So it just shows how sensitive it truly is. We can move on. And after we get the data collected, we run our data into a code. We do something called the Fourier transform, which Dr. Zenelin explained a little bit. And with that graph, the peaks that you see, that's how we can calculate the resonant frequency of the pendulum. And after we gather all of this information, we can go back to coding. And that's how we're going to create a model for adding control systems to the pendulum. If you want to have a better idea of control systems, picture when you're driving your car and you set it in cruise control, your car is going to move at that certain speed. And if you need to speed up or slow down, your car is going to do that by itself. Like you don't have to touch anything through control systems. So that's what we're planning to implement to the pendulum, so we can kind of control that noise and hopefully reduce it. We haven't gotten to that part yet, but our goal is to like use a bunch of different models to see which one gives us the best results, and hopefully give that information to LIGO to help the detection of the gravitational waves. Okay, this is all I have for my part. Thank you.
Thanks very much. So we're getting continued great questions in the chat. Before we get into the Q&A portion for our three panelists, we do need to present a brief slide from admissions. So why don't we go ahead with that?
Okay, everybody. My name is Mara Miller, and I'm the Associate Director of Admissions at the Prescott, Arizona campus. So if any of you out there are seniors in high school, we are still accepting applications for the fall, so it is not too late to apply for this fall if you are interested. Otherwise, if you are a junior or younger, the application for admission for the following year should open up around the summer after the completion of your junior year. It is an online application. You're going to submit the online application and have a transcript from high school with end of junior year grades submitted to us. That's the only thing you have to send to us. If you would like to include SAT or ACT scores, you can send a report, but it's not required. So if you don't really feel like your score are an accurate reflection of what your abilities are, then you can just opt out of sending it. We don't require an essay or resume, letters of recommendation, but you're welcome to send those items to us as well. I know in the chat a lot of you were asking about admissions requirements, so let me touch on that as well. So for all of our technical majors, which does include the astronomy and space physics programs, as well as engineering and a number of the other majors we offer, you're going to take Calculus 1 the first semester that you enter into the program. So we want to make sure that you are set up for success. So at a minimum, you want to complete pre-calculus in high school. We also require that you do 2 lab science courses, which would be like biology, chemistry, or physics, and one of them must be chemistry or physics. Now, we only require one of those, but I would say that doing both of those in high school would be the best for you. Um, but we only actually require one of them. If you are accepted for admission, we are automatically going to consider you for a merit scholarship, so you don't need to complete a separate application. As you can see here, there is a code, so if you want to jot that down, you can utilize that when you are ready to apply for admission so that you don't need to submit the $50. If you do have any additional questions about admissions, you can throw them in the chat or feel free to reach out to the admissions office at any time in the future, and we're happy to help you out.
Okay, thanks a lot, Mara. I think at this point we're going to move into our panel discussion. So we have many questions to address. I'm afraid we won't be able to get to all of them, but as Mara mentioned, a lot of the questions in the chat are about the requirements and preparation that students can have in high school if they're interested in astrophysics or related fields in engineering and the like. So I did want to pitch that to our panelists as well. What sort of things should high school students be doing now in terms of preparation for math, computer coding, and the like, if they want to prepare themselves for a career in astrophysics or a related career in engineering or the like?
How do you want to go for the question that you point to us one at a time, or how do
Why don't you get us started, Dr. Zanelin?
Yeah, my personal opinion is that almost everything will be done very rigorously once you are in college, and there are possibility to start doing some good things in high school, and obviously learn integrals, derivatives, some background in math is going to help. But my experience is that the level of physics you do in high school is so different to what we do, which is good to get started. But don't expect it to be too advanced compared to what we expose you. We like to build the background of people up from scratch. I noticed one question I'm going to touch right away about the opportunity of research that people can already do for high school. And I know we have some high schools here in Arizona where you have a full semester off at the end of the senior year. And we had sometimes intern that spend a full semester working here. And one I have right now is actually working on a paper that is going to be a journal publication, and is going to a NASA conference with that. So these are really good opportunities. And this person took some AP math that was helpful, and he also learned a little bit of coding with Python. But I would say the most important thing is to take courses and read things that help you to understand if this is something you're interested. And then come if you come with us. So no, we can obviously we will help you to reach the level you need to be able to be productive. And so that's my take for this.
Thanks. Dr. Grederson, do you want to comment either on preparation or opportunities that may be available for high school students?
Yeah, preparation, I second. You will be able to build all the skills you need here. If you have the opportunity to take a programming class, that kind of skill coming in will just help you. So I encourage you to take physics as high a math as you can and programming in high school. We've had some high school students I know work out at like the observatory. I haven't had any in my lab, so I'm going to refer to Dr. Zanelin on that one.
Yeah, as I said, I had so far 4 or 5 high schoolers that stayed here for an extensive period of time. I also work occasionally with high schoolers in the Navajo and Hopi reservation. But they can get a paper or something that can they can use as a start for anything they want to. Usually, if the interaction is a little bit extensive, meaning that they come here in person at least for a week, and then we can start something remotely. But it's a little bit on a case by case basis. Not that is a guaranteed thing. So that's what I wanted to say. And the other thing that I wanted to mention that is interesting, not just for the high school experiences, but also for the degrees we offer in physics and astronomy, is that the for water guard gravitational wave, this research is only offered in the Prescott campus. I know there are experimental research opportunities in the Daytona campus, but I know what we cover today is specifically offered in the Prescott campus because the professors are here. It doesn't exclude the student from the Daytona campus to come here and do research. And I had a couple of students that were with the Daytona campus, and they came here and for the summer, and we did the research together. So, but I know the center of mass is here in Arizona.
Alice, your perspective on this is probably a little different. Do you have anything you want to add?
About the classes, I would like to add that this is a very math heavy course. I feel like I catch myself being grateful because I'm a little more advanced in math than in physics at this moment, and there's a lot of derivations. So I would say it's really important to come with a good understanding of math. Um, you learn everything you need here. Like mentioned in your very first semester, you're going to start with Calculus 1. So from there, you learn everything you need. But I would say coming in with a good math background is important. And I would also say that if you guys are interested in coding and coming in with a good coding background will also make a difference. This the degree has its own coding requirements. The coding language that we do right now is Python. And I would say it's very, very important. It helps me out so much in the labs during classes and especially in research. So if you came here with a good coding background, that would also help you a lot.
There is also another thing I wanted to mention, Brandon, if I can take a second. And one way where we are unusual here at Embry-Riddle, but and in Prescott too, in particular, is that we have a lot of people that come from very high level institution, and I come from MIT. Brandon comes from MIT, and we have people from Caltech, but we spend a lot of time with undergraduate students, and we really like to interact with people. So if any person that is on the chat now, and your future is very important, feels that, oh, you know what, I think it could be a good investment for me to fly or drive to the campus for a day or a few hours, and we would love to have a chat with you. You can come, and we can share the labs. We can show you what we do with the students. I know it's such an important decision that sometimes I know spend a little bit of time face to face in front of a coffee and can give you some feedback that I know you might not get just by watching a seminar. And one of the things that we really want to convey is that we do spend a lot of time. I know we in our physics and astronomy program, we have I know pretty much I would say currently about 50% of the students do research, with the faculty. But I know the motto is that anybody that really wants to do research is able to do research with some of us.
Sometimes enthusiasm for wanting to do research is going to get you farther than, being the best at math or anything like that. Uh, Having an enthusiasm and a passion for what you're doing is really important. And communicate with us. Shoot us an email if you are interested in something that we're doing, because we would love to talk to you. And I know that sometimes that's the hardest part, cold calling somebody, but we really are happy to have that conversation and show you around at least. So.
Yeah, thank you. Yeah, talk to us if you want to talk. I know I have a three teenager children, and I know it's a privilege when they choose to talk with me. It's a rare privilege.
So I did want to add on, there are a couple questions about the differences between campuses. What admission says is absolutely correct. With our department, we have made sort of a distinction where we've sort of split space with the Daytona Beach campus. They get the upper atmosphere out to Mars. We get Mars and beyond. So their space physics is focused more on human exploration, physics of the upper atmosphere, space physics, and the like. We're focused more on what would conventionally be called astrophysics, including gravitational wave astronomy. So basically moving, beyond our solar system, trying to understand the more distant universe. So there's many good research opportunities at both locations, but the focuses on the two campuses are different. We've got a few questions on what one does with a degree in astrophysics, astronomy, or space physics. So would the panelists like to
And yeah,
address some what career opportunities look like?
yeah,
Starting with Dr.
let me
Zanelin.
address it because I at least give my take. I know I've been observing this thing for the last 25 years in one way or another. So there are many beautiful opportunities, and I know in academia, in the private sector, and even in teaching if someone wants to. So in academia, there are you can try to become a professor, or you can try to become a researcher, which is similar to the professor, but you don't have to teach. And you can do it in government laboratories or even in universities. And I would say this is a fraction of our students that like to do that. Usually that path requires to go for a PhD, which is actually a really fun experience, I think. And in the private sector, our graduates, they have skills that are enormously useful. And I'm going to give you an example. I know companies like SpaceX, I know they hired one of my friend that has experience in LIGO just to design a laser system that was tracking the separation between different satellite to come up with a system. How do I attach to each other? But I know there are companies that every company that has engineers, they typically hire physicists because they have a swap. The skills can be swapped in terms of coding, in terms of mathematical modeling, in terms of experiments. I would say that physicists are also appreciated because they are able to do install solutions that are not off the shelf. If there is no piece of equipment or no codes that does exactly a certain solution, physicists are very comfortable to doing that. And I can say that the number of our graduates that has a job that related to their skills, I know after 1 year is extremely high. I mean, in middle 90%, I know, so it's very high. We do have students that at certain point they realize that they love teaching. They like the routine of a teacher that I know teaches for 9 months and then in the summer does different activities. So I would say it's a small fraction, but some people decide to become high school teacher, and I think it's a wonderful career. My sister is one of those. So I think these are the three directions. Sometimes we have creative I know directions. People that use their coding capabilities to stock exchange. I know they hire physicists for something called Markov chain Monte Carlo that we use in our simulation to predict the I know where stocks goes. The salaries are extremely high. I'm not sure it would be my cup of tea, and but I would say that everything that involves technical skills, STEM technical skills, we have good opportunities that come up. I know I had one of my former students has been hired today a Boeing to do the modeling of the vibration of the infrastructure of an airplane. So there are a broad range of opportunity, and people respect a lot graduates from this university. I know because the reputation we have is that people develop real skills and that are useful for companies. So I would say Embry-Riddle is very respected as a degree.
Dr. Gretterson, anything to add?
Yeah, I think you have a couple of different options. So I had dual majored as an aerospace engineering and physics major when I was an undergrad. And after undergrad, looking at what to do, I know that a lot of the engineering companies like Raytheon, places like that, were really interested in having that physics background because it teaches you to think in a slightly different way than most of their engineers. So that's very marketable, and we have a lot of students that can't go that route. We've had students in our lab hired by uh, Raytheon was a big one this last couple of years, but Boeing, other places like that. You can also work as a technician at labs or go into the private sector as well. I, of course, ended up going on and doing my PhD, and I was at a couple of national labs, so Lawrence Livermore and also at NIST. And many of these places have all sorts of different levels. So whether or not you choose to go on to higher education to grad school after your undergrad, or if you want to go and work, there are definitely opportunities at both those levels. One of my friends at NIST, he barely made it out of high school, ended up wanting, he was just interested in what they were working on over at NIST, asked if he could come and took a kind of a, he didn't even have a finish his university degree before he started working on a project there. And it was just his passion. And NIST kind of pushed him into finishing his degree and eventually getting his PhD. But it was all kind of along this kind of non-traditional track. So there are certainly opportunities out there that aren't, this track that we all by definition took of undergrad, graduate school, become a professor. And I think that there's a lot of really cool things out there that you can do that maybe we don't always see, both in, NASA, some of these national labs, but there's private businesses as well. A lot of really cool stuff that they do. So.
Alice, you're a bit early in your career, but do you have anything you'd like to add?
Um, I don't have anything to add because I'm so early, but I would say that this is where research came in for me. It took me a really, really long time to figure out what I wanted to do for in university, and I have always been really interested in physics and astronomy, so I decided to give it a shot. I was still a little bit unsure of which path I would like to take. And after I came to Embry-Riddle and I started doing my research, I have a much more clear path in front of me now. I think, I don't know, I just found a direction. So this would be my biggest thing. Like, if people would like to come here, research has really changed my intentions with my degree and what I would like to do in the future. And I would also say that we have amazing faculty here at Prescott. I have been helped in so many ways. I would say especially by Dr. Zenelin and Dr. Huey. Since it's a smaller program, I would say everybody is really personable and really, really wants to help. um, as a student, if you are interested enough and if you do your job, if you try to make those connections, this is such a great place for your degree and for your future career, because people here really are really willing to help you out and will make it happen for you.
Thanks so much. We are over an hour into our presentations. I think what I'd like to do is pitch one more question and then leave any closing statements that the panelists would like to make. So I want to focus a little bit more on the astrophysics of it all. So Isaiah asks, what specific understanding of physics is most utilized in understanding gravitational waves? I know Einstein's gravitational theory is used, but does it utilize more conventional or quantum level physics?
Yeah.
Starting with Dr. Zanlin.
Yeah, so let me say a few comments about it. So the reason why I am interested in this field is because it helps me to understand at a fundamental level the physical laws of nature. And general relativity is one aspect of that. But I know for people might have heard about photons, and meaning that electromagnetic waves at the microscopic level are made of elementary particles called photons. And people are also speculating that gravity might be made of gravitons, the equivalent particle. And so there are directions that are being explored and are explored in understanding quantum aspects of gravity. And as a matter of fact, I know we have at least two or three faculty here that are exploring that, not full time, but part of the time. And I know we've already published two or three papers on the topic, and more are on the way. So, and in some regard, these gravitational wave interferometers are places where gravitons interact with photons, which is one of the most fundamental process of nature that is not completely understood. And so this gives you a perspective of the kind of question you would be able to answer. And I know at a deep level, so the message I also wanted to convey about it is that I know with a degree here, you will have a lot of job opportunity no matter what path you choose after. But the most important thing that was the question that I wanted to be addressed when I study physics is that will this degree allow me to understand at a deep level how God made nature and what are the fundamental mechanism of how nature works and gravitational waves and is a wonderful field because there is still a lot that can be learned from that. You know, we just discovered this wonderful gold vein, and there will be a lot of fundamental aspects of nature that will be explored with that. It's really amazing, you know, so there is one of my colleagues at MIT just became the dean of science at MIT, and she was saying that people should choose physics not because they're good at that, but because they like it, they are fascinated by that, and if you have a curiosity of understanding nature, I know you're going to find plenty of nerds here that will want to work with you on that. Sometimes I like to describe it as a school of Jedis, but I think it's okay to say that I know we are very passionate in trying to understand the fundamental aspect of nature. And even if gravitational wave have a lot of aspects of classical general relativity and classical physics, but the lasers are highly quantum in behavior, and we have to take that into account in all the detail working of the interferometers and even gravity itself as possibly quantum aspects that we will include.
Thanks, Dr. Zanlin. Dr. Grederson, anything to add?
Yeah, I think he answered that pretty well, but I would say in this field, it depends on which aspect you're looking at also. So you're looking at this overall. Michaela answered it for the overall, but I think as soon as you start to really look at the different pieces, it's a really rich field. Are you trying to understand gravitational waves from what sources? Are you looking at how are these created? Are you trying to come up with models for something we can look for? Are you looking at a signal we have and trying to get as much information out of it as possible? Are you doing the material science to understand the mirrors or whatever, feedback systems? There's so many subfields within this field that what specific understanding of physics it'll depend on what exactly you're looking at and kind of what scope you're trying to look at. So,
Thanks, Dr. Grederson. Alice, anything to add?
I don't have anything to add.
Okay, I think we're a little over time here, so I would just like to give our panelists opportunity if you have any final thoughts. If not, that's okay too. But anything else you want to say, starting with Dr. Zanlin?
Yeah, the only thing I wanted to say is that it's hard to figure out everything in an hour. If you have questions, contact us, and if you come and visit us, we will be very happy to show you around and talk more extensively.
Dr. Grederson?
yeah, I hope that we get the opportunity to meet you. Don't be afraid to ask. If something is interesting, it doesn't have to be necessarily your goal to work in a lab or something like that, to ask for information and just try and understand things that are interesting to you, even if it doesn't end up being your long-term goal. Also, don't be afraid to try new things. If you join a lab and you're doing something, and we've had students who start on a project and then they realize, oh, this isn't quite what I want to do long term, but they've learned something interesting and they have that information going forward, and hopefully it kind of steers them to what they do want to do long term. So the most important thing is just to communicate and get started.
Alice, anything to add?
I just like to say that, speaking from experience, you don't need to have everything figured out right now. If you're willing, things will work out your way. Just choose to do something that you're interested about and that you're passionate about. And I would say that if you guys choose to attend Embry-Riddle, you will be very happy here. It's a very nice, very helpful environment.
Okay, thanks so much to all of our panelists, and thanks so much to Mara and McKenna and everybody in emissions and marketing for facilitating this. I think that concludes our webinar for tonight. Thanks especially to everybody who's in attendance and for all the great questions. Hope to hear from many of you down the road. Goodbye.